Congratulations, you made it to our final unit here, nuclear chemistry. Now, the one thing that makes nuclear chemistry different from all the other chemistry we studied this year is that it involves the nucleus. Everything else we were looking at involved the electrons, transferring electrons, sharing electrons, etc. But with nuclear chemistry, we're going into the nucleus. And all our nuclei have protons and neutrons in them, except hydrogen. Most hydrogen atoms just have a proton in the nucleus. And these protons and neutrons are held together by a very strong force acting over an extremely short distance. Remember, our nucleus is really small, very dense. That's where all the mass is, and that force holding them together is strong. We know that because when we split an atom, we get a ton of energy released. Now, these are the two ways that we can represent an atom symbolically. If you remember from when we did our atomic information chart, here we have an atom of tellurium. The top number is the mass number. The bottom number is the atomic number. And then over here we have radium-228. The 228 again is the mass number. So we can refresh our memory. If I look at my symbol for tellurium, how many protons are in that atom? It's simply the atomic number. So there are 52 protons in that atom of tellurium. How many neutrons are in there? Well, that's when we have our symbols set up kind of like a subtraction problem. So when I subtract 122 minus 52, that tells me that there are 70 neutrons in that atom of tellurium. For the radium atom, how many protons? Well, you're going to have to go look on the periodic table. When you look at the bottom of group 2, you see Ra is radium, and it has an atomic number 88, so there's 88 protons. So how many neutrons? Well, you have to subtract out the 88 from the 228, and you get a $140. So that's just a refresher. We're going to be writing some nuclear reactions using those different symbols, and so just wanted to review that with you. Now, what is the key aspect, or key to many aspects of chemistry? That would be stability. We've talked about that all year. Elements want to be stable, like the noble gases, so they bond and do different things because of that. Well, same thing with nuclear chemistry. Isotopes, atoms out there in the world, want to be stable. And so their goal is to end up on this band of stability. When we have smaller atoms, like from atomic number 1 through 20, then we typically have a 1-to-1 ratio with our protons to neutrons. For our larger atoms, like mercury, for example, mercury has an atomic number of 80. 80 protons, 80 neutrons would be up here on this 1-to-1 ratio. That's not stable. When you have that many protons in a small spot, they're all positive, like charges repel, you need more neutrons in the mix in an effort to maintain stability. So the band of stability is way up there, so 120 neutrons for mercury is stable, and that's why mercury's atomic mass is around 200. Anyway, isotopes of these atoms want to be stable. They want to be on the band of stability, because if they're not, they are what we call radioisotopes. Radioisotopes, they are radioactive isotopes. They are so because they are unstable. They have a bad neutron to proton ratio, aka they're not on that band of stability. Because of that, they will radioactively decay. And this is the process that we'll look at when an unstable radioisotope loses energy by emitting radiation. And as we'll see, radiation can be in the form of particles or energy or both. And what exactly is radiation? The penetrating rays emitted from a radioactive source. And each type of radiation has a different level of penetration power, and so we will check on that as well. Overall, this process through which an atomic nucleus gives off those rays is called radioactivity. So again, we have radioisotopes. They are unstable. They're not on this band of stability. So because of that, they will radioactively decay, giving off radiation through a process called radioactivity. And as Lisa in your notes packet points out, this is that unstable radioisotopes of one element are transformed into stable isotopes of another element spontaneously and exothermically. Exothermic, we just talked about again last unit, releasing energy. Okay, so there you see in the diagram, energy being released. You can actually feel some warmth from certain radioactive materials. And spontaneously, this happens all on its own. We don't have to do anything to radioactive atoms to get them to emit radiation. It happens on their own. It happens at a predictable rate, but not every atom is very predictable with when it's going to emit radiation and try to become stable. Here's another example of a spontaneous and exothermic process from a classic cult movie. Girl's head spins around. I don't know if you've ever seen it or not. See if you can figure out what movie that is. Spontaneous combustion. All right. So let's look at these different types of decay. And this is how these radioisotopes are going to try to return to the band of stability. First up, we have beta particles. If your nucleus has too many neutrons or protons, then again we have that bad ratio. And if there's too many neutrons, we can convert one to a proton by emitting a negative beta particle. Now again, you got through this whole year, protons, neutrons, and electrons are not the smallest things out there. All right, beta particles is a little negative part of the neutral neutron. So if it gets rid of its negativity, it becomes positive and turns into a proton. Penetration-wise, you can see here that it's a light particle. It can penetrate human skin, but it can be blocked simply by metal foils, wood, like the structure of your house, etc. So what we do when we do this beta decay is I simply subtract the particle out. So here we have a radioisotope of cesium. 137 minus 0 is 137. So the mass number is not changing. 55 minus negative 1 is 56. And so we see that we changed a neutron into a proton, and we have now changed into an atom of the element barium. And that is a much more stable situation than the cesium was, so it spontaneously happened. Positron. If there's too many protons, then we can change a proton into a neutron by it emitting a positron. Again, same penetration power as a beta particle, it just happens to be the positively charged particle. And so again, I just subtracted out. Here we have a radioisotope of iodine, 121 minus 0. Again, our mass number is not changing, but our atomic number is. 53 minus 1, because we're losing a proton, is 52. And we have now changed into an atom of tellurium. A large particle that is typical of coming out of our larger unstable radioisotopes is an alpha particle. Our nucleus has too many protons and neutrons, and so this large chunk, large atomically speaking, comes out of the nucleus. It's essentially the size of a helium atom, 2 protons and 2 neutrons, and so we give it the symbol of 42He. And so here we have an atom of plutonium, and when we get rid of the alpha particle, again, just subtract it out. 210 minus 4 is 206. 94 minus 2 is 92. So this atom of plutonium has now become an atom of uranium. And these alpha particles, as you see there, they are large, so they can't penetrate your skin. However, if they got into your soft tissue, they can cause some internal damage. So if someone ever offers, hey, you want to drink this supply of alpha particles, say, no thanks, I'm good. All right. Gamma radiation is high energy particles, okay? And these gamma rays are what give nuclear science the bad rap, because yes, these this gamma radiation can mutate cells, can turn regular cells cancerous, but it can also help combat cancerous cells too by mutating them back or destroying them. But this gamma radiation is dangerous and very high energy. If we have a nuclear equation, then we're simply going to use the symbol for gamma from the Greek alphabet, and it looks like that. Now it's because of this gamma radiation that again we have the horrific images of after a nuclear bomb explodes. And back in the day, you can ask your grandparents, we have fire drills and tornado drills. They used to do duck and cover drills. So if you go to YouTube and search duck and cover, you can find an awesome public service announcement based on it. I'll just show you a small little snippet here.
Remember what to do, friends. Now tell me right out loud. What are you supposed to do when you see the flash?
So if you want to see the full service announcement from Bert the Turtle, then like I said, search on YouTube for that. Alright, the last part of this video are these transuranium and transmutation definitions. So transuranium elements, these are all the elements after number 92. Remember, uranium number 92 is the largest naturally occurring atom on our planet element. And so everything after that are all man-made and radioactive, with the first ones being created in 1940, neptunium and plutonium. And what we're seeing here now are these transmutation reactions. And what that is where chemistry came from, alchemy, trying to change metals into gold, trying to change elements into different elements. And that's what nuclear chemistry does. Converts an atom of an element into the atom of another element. And so all of our decay reactions like we've just seen. So here we have Einsteinium-252. It's going to decay emitting an alpha particle. So what I do, I draw my arrow for my Einsteinium, and then it's emitting an alpha particle. And so I just need to subtract that out. So 252, put the plus sign there, 252 minus 4 is 248, and 99 minus 2 is 97, an atom of berkelium. Now the other type is where we actually have bombardment here. And that's how we make a lot of our large new elements, is that we take an element and bombard it with neutrons. It gets sucked into the nucleus and we create a larger element. But for example, here we see that plutonium-244, it's going to absorb a neutron. And so this is our symbol for a neutron. You might remember from back in the atom days, and I'll give you these symbols on the nuclear equation sheet. But it absorbs a neutron and then emits a beta particle. And that's our symbol for the beta particle. And so now we have to do some heavy-duty math here. 244 plus 1 is 245. So that's on this side. Minus 0 is 245. So the new isotope has a mass number of 245. 94 plus 0, we're still 94 on this side. 94 minus negative 1 is 95. And so now we're an atom of the element americium. So this should help you with completing those nuclear equations. And remember, that's due in a couple days from now. All right, see you in the next video.